this section in pre-cal. I do this section in like 2 days. So your book puts a couple things together. So we're just gonna see how it goes. But I think you guys will be fine. So Friday, we talked about what the logarithm was. And so just to remind you, if I have log base 2 of 32, what does it equal? 5. Why?
You drop a log.
Yeah, because how do you drop a log? You give it a swirly. That's exactly right. So this is what we learned on Friday. Swirly math. So 2 to the power of 5 equals 32. And that's why. Okay? So we don't work in logarithms typically. We think in powers because we're better at that. Okay? So that is the swirly to convert into exponential form. And these two statements are equivalent. They mean the same thing, just written different ways. Okay? And so we want to know log base b of 1 equals what?
0.
0. Very good. Why? Because base to a power of 0 always equals 1. And again, that just goes to our swirly again. How do you drop a log? You give it a swirly. Same idea. So because b to the 0 equals 1, any number to a power of 0 equals 1, whatever that base b happens to be. All right, so with that in mind, log base b of b equals 1. Why? Because anything to a power of 1 equals itself. Again, yeah, if you give it a swirly, it makes perfect sense. Okay. This is kind of an interesting one. Log base b of b to the x equals x. Very good. Why?
Because x times
b to the x equals b to the x. That makes perfect sense. So b to the x equals b to the x, which is kind of an interesting thing. I think you had something like log base 12 of 12 to the 51. I don't know what it was. Equals what? 51. Yeah. Because 12 to the 51 power equals 12 to the 51 power. All right. Really, log base 12 of 12 sort of cancels itself out and leaves a 51. Another way to think about it. We're going to learn another way that works today. So very interesting. So here we have some notation here. You don't know this yet. So log base E. What is E? Euler's number? Not quite 3. Very good. What is E? Not quite 3. That's right. So it was 2.71828. Yada, yada, yada. Irrational number goes on forever. And that's all fine and dandy. But what we want to do is we use this a lot. Base E. Okay. And so we have a shorthand. So anytime you see log base E, we're going to trade it in for natural log. This is ln is called natural log. And please don't say Ellen, because Ellen has a TV show.
Ellen? Oh, that's right.
All right. So we're not talking about the TV show. We're talking about natural log. You have a natural log button on your calculator. This one is here on this calculator. And so you could look at like the natural log of 2 is 0.693, blah, blah, blah. But, that's kind of meaningless, so we'll use it later. But this is what this means. If you ever see natural log, we can trade in the natural log for log base E. So we can change the notation to help us out. Okay, so they mean the same thing. Log base E is the same as natural log. Log base 10. Again, we have some notation here when we say log base 10. Log base 10 is called the common log. And common because we have a common base 10 number system on planet Earth. Okay. And so we call it the common log. And basically what that says is, hey, we're lazy. So instead if you see a logarithm without a base, we assume base 10. Okay? So log of x means log base 10 of x. Okay? And that's really important that log of x does not equal log base 1 of x. Okay? It's because the base couldn't equal 1. We had conditions on b. Okay? So there you go. So this is called the common log, and again, that button is on your calculator as well. Just the log button, and that is base 10 because your calculator is base 10. Everything we do in lots of different bases. What are we doing today? Oh, okay. Properties of logs. All right. So basic understanding here about logarithm, and so it turns out that logs and exponents are very closely related. Okay. And so we have properties that apply to logarithms, and they're very similar to properties that we have for exponents. So here are our properties of logarithms. The formatting got all funky. That's okay. So there are 3 properties. I mainly talk about the product property and the power property. Turns out the quotient property is superfluous. Superfluous.
Was it
Extra.
supposed to be a
Unnecessary. No. No, this is a good word. I like saying it.
joke? Okay.
Are we just writing these down? Or are we writing something underneath them?
We're going to write stuff in. So leave a couple lines of space between would be good. All right, so properties of logarithms. The first property is the product property, and it is a product, meaning I have, if I have something that says log base b of u times v, 2 things multiplied together, trapped inside a logarithm. It turns out that I can expand it using addition. It's the same to write log base b of u plus log base b of b. So this is the product property. It allows us to add 2 logs together. Okay. And the converse is also true. If you have 2 logs added together, then you can shrink it down into a single log with a product in between. Okay. So why? The reason as to why comes back from our exponent logic. X cubed times x to the 5th. If they have the same base, what are we allowed to do in a product?
Add them up.
Add the logs. And so it's x to the 3 plus 5. So we're allowed to add the exponents, where here we're allowed to add the logs. Okay, so they're very closely related. All right. The quotient property, again, quotient implies what? Division, sure. So if we have log base b of a division problem, u divided by v, then we can expand it and make it a lot longer. What do you think we're going to do?
Subtract.
Yes, we are. We're going to subtract the logs. Log base b of the top minus log base b of the bottom. And that's what we call expanded form. Because it's bigger, right? It's expandeder.
Yeah.
Okay. Lots of logs. This is single log. We call this expanded. And we call this side condensed. Condensed because, yeah, it's smaller, right? Makes sense? Okay, so again, where does this subtraction come from? What is it similar to? Our exponent properties, yeah, if we have x to the 5th divided by x squared, if they have the same base, what are we allowed to do? Subtract top minus bottom. All right, So the same, it's all very closely related. All right, and the last property is the power property. I lovingly call this the power play. Log base b of u to a power p. Log base b of u to a power p. If you have something with an exponent and there happens to be a log in front, then it turns out that that power just gets to drop down in front, p, and multiply log base b of u. And really what's happening is we're just doing this sort of repeated addition a whole bunch of times, if you think about it. But I'm not going to go into why. That's called the power play. The same is true if you have a number in front of a log. It came from its power position. So you can slide it back up to condense it. All right, so this is what we would call expanded form. And over here is the condensed form. Okay. We're going to go both directions. We're going to figure out how these properties work. And it's important for us to know how they work so that we can use it to help us solve some equations. Okay. All right, so products property, quotient property, power property. All right, example 1, expand. What does expand mean? Make it bigger. Yeah. Make it bigger using properties of logarithms. I have one rule. And that one rule is use exponents. As much as we can, we want to use exponents. And I really like this section just for remembering our exponent properties because calculus is all exponents and fractions. Okay. And so we want to be really good with them. And so I don't want to see any radicals. I want to use exponents. So here I have log base 5 of x to the 4th, y to the 5th times the cubed root of z. This is a giant product. So this is x to the 4th times y to the 5th times the cubed root of z. So what do you want to do? Yes. This cubed root of z we can rewrite using exponents. So we absolutely want to do that. X to the 4th times y to the 5th times z to the 1/3. Okay. We don't want to see any radicals. We're going to use exponents. Now, this is a giant property, giant product. So what property can we use? The product property. Very good. And so what that means is we get to add up a bunch of logs. That's going to be log base 5 of the first thing plus log base 5 of the second thing plus log base 5 of the third thing. Lots and lots of logs. All right. Good so far? All right. What else can we do?
Take the exponents off of it.
Yeah, the power play. If we have a number with a power and a log in front, we get to drop our powers to the front of their own log. Okay. And so each of these powers gets to drop right down in front of its own little log and multiply. So yes, that is another way to write it. I'll write it out. So we would say 4 times log base 5 of x plus 5 times log base 5 of y plus, I could write 1/3 log base 5 of z. And it would be equivalent, what Trinity I think was saying was, would it be equivalent to say log base 5 of z divided by 3? Yeah. Yes, it's equivalent.
Is there a preferred way you want us to write
I'd go just with the 1/3, frankly. Yeah. So this is our fully expanded form right here. It's as big as it can get. Okay. Right here.
Of the next.
That's Ellen.
Natural log. Oh, yeah.
Oh.
That's actually natural log. Which is fine. It is, what is natural log equal to?
2.
Log E.
Log base E. Very good. So if we wanted to, we could rewrite that natural log as log base E, but I'm just going to use natural log because it's only got 2 characters instead of 4. But again, I want to use exponents. Now, when you look at this natural log problem here, what do you see? What operations are you seeing?
Quotient.
Quotient. Okay.
And product.
And product. Good. So you have a giant quotient because we have this giant division sign. Now I told you the quotient property happened to be pretty superfluous. Okay. It's actually not necessary, and I don't really use it. Okay. And the reason I don't use it is because I would rather just use exponents. So I'm going to rewrite this entire argument here using exponents. The natural log of, this is x to the first times y cubed. What can I do with this cube root of a? How could I rewrite that? Okay, a to the 1/3. How do I bring it up from the denominator?
A to the negative 1/3.
Yeah, very good. A to the negative 1/3. That negative exponent can pull it out of the denominator. Okay. And then what can we do with the square root of b? B to the negative 1/2. Very good. All right. So you can see I can take that quotient and just turn it into a giant product now, isn't it? Yeah. And then so I don't actually have to worry about the quotient property, which turns out to be really confusing. People lose negatives all the time when you use the quotient property. So I much prefer you to go this direction and rewrite it just using exponents. So now we just have a giant product. How are we going to expand that, do you think? Natural log of x plus natural log of y cubed plus natural log of a to the negative 1/3 plus the natural log of b to the negative 1/2.
Are you going to put it as well?
Is that a problem in your book? Okay. All right. What else can I do on this problem?
Power play.
Power play. Power play. Love that. So our powers are going to drop in front. You'll notice, where does the quotient property have subtraction? Where does the subtraction really come from? Your negative exponent. That's exactly right. So we have the natural log of x. Here, that 3 drops down. That's going to be 3 times the natural log of y. And what happens with our natural log of a? Minus 1/3 natural log of a. Good. And the last one? Minus 1/2 natural log of b. Excellent. And this is fully expanded, and that's a great final answer. Okay.
So can you skip?
Can you skip? Good question. Absolutely. This is how it's written in your book, let's say. The original problem you can write down looks like this. So this would be my first line in my homework. And then I'd go from this step right here, that's what you write down originally, to my final answer. Okay? Can you do that in your head? Yeah, right? So I absolutely want you to do as little work as possible. Okay? Especially on this stuff, it turns out the more work that you do, the more mistakes you're going to make. Okay? So with this in mind, using exponents now, we expanded everything. What do you think we're going to do next? Condense it. Okay? And so same idea here. If we take something like letter B here in fully expanded form, I want you to be able to do this in as little work as possible. And so you'll notice when we condense back to a single logarithm. Only one. All right, expanded, we've got 4, 5, 6 different logs. But condensing, we're going to condense back to a single logarithm. And then what you need to be able to do is, hey, what do we do with this number 3? Where did it come from?
Y cubed.
The power. So we're going to push our coefficients back up to their power position. And then tell me about, like, if this becomes y cubed, because that 3 moves back.
Yeah.
Then all we have to think about is this argument here, which was a fraction. And then we just have to decide what goes on top and what goes on bottom. Negatives on the bottom. Brilliant, my friends. Positive arguments on top. Negatives on the bottom. Makes sense, right? Totally easy. That's what we want.
Awesome.
Okay, so here we go. Example 2.
Right.
Condense the expression to the logarithm of a single quantity.
Don't sleep in class.
There's a few people who have a hard time staying awake with experience.
Get up.
My husband has the easiest job.
You say it when dad.
What?
You say it when
Are you kidding? That's the hardest job. Stay-at-home mom, stay-at-home dad, worst job
I would
ever.
not say that's the hardest job.
It's the
I
hardest
would
job.
say it's a hard job. but
It's
not
definitely the
hardest.
hardest job.
Now you beat your kids enough, they'll learn how to.
Oh!
I can use that point.
I'll be honest with you. I'll be honest with you. My stepdad just left him, and I took care of my little brother, and I was wake up when he took a poop, and I was like, you go back to sleep.
He gets to come home for lunch every day, and so he'll eat, and then he'll like take a nap.
Serious?
And then go back to work. He's a director of IT.
You corrected it.
IT, informational technology. He's a network and like he does computer stuff.
Hey,
You
that's
need
a
to
whole lot of
socialize
customer
with people.
service. Yeah, that's a lot of doing this.
Miss,
Miss, that's a whole lot of customer service. I don't know if we can.
What do you call what I do? A whole lot more customer service.
Yeah.
Okay. Example 2, condense the expression to the logarithm of a single quantity. And another way to write that is to say condense the expression to a single logarithm. All right. So the first thing we have here, 1/2 log base b of x minus log base b of x plus 4 log base b of y. What do you want to do first?
Does keeping exponents apply for this as well, or do you want us to put it back into?
I'm totally good with keeping exponents, and your book might convert them back to radical form. They're the same. They're equivalent.
I don't
So
know how far you.
yeah, we'll see. All right, so we have a couple numbers in front. We're going to push those back up to their power position. You'll notice it's log base b. That has to match. They all have to be the same base. Okay, we can't do this if they all have different bases. So I'm going to write a single logarithm of base b of some argument. And that argument is going to have a top and a bottom, a numerator and a denominator. And we just have to decide what goes on top and what goes on bottom. So this is not x. What is it really?
X to the
X to the 1/2 or square root of x, true. And so does it go on top or bottom?
Top.
Top. I'm just going to go ahead and leave it x to the 1/2 for now. All right. This is x, but there's a negative in front. Where does that go? Oh, yeah, that's from the denominator. Oh, that shouldn't have been an x. All right, that's a typo. It should be a z, but that's okay. Pretend it's a z, but I'm not
Oh, I
going
was
to.
looking at it, I was like, alright.
Oh, you're not adding the here.
So you could move the negative one back up, but it's not necessary. And then here, this is really y to what power? Does it go on top or bottom?
Top.
Yeah,
Your lowest was easy?
that's it.
The bottom X.
Yeah, this should be a z, and I don't want to make this more complicated than it needs to be, so a z would be better. And so this would be a perfectly wonderful answer. you'll see we have the logarithm of a single quantity. That's one giant thing there, all multiplied together. If you wrote log base b of the square root of x times y to the fourth over z, this is also a perfectly wonderful answer. They mean the same thing. They're equivalent. One is not better than the other. They're the same.
So what if you just had all the exponents out? Would you want it like that, or would it all be just one line? Like z to negative?
I don't move the negative. I only move the actual number.
Well, I know that.
Yeah.
I'm just saying, if you, how you did earlier, just made it all one on the line after you take out the log.
Oh, I see what you're saying. Oh, okay. I'm with you now. So you're saying if you leave it x to the 1/2 times y to the fourth times z to the negative 1.
Yes.
Yes, that's also equivalent and also perfectly wonderful. All right. So the tricky part on this is going to be, what does my answer look like? Right? Because your tests are multiple guess. Does your answer match one of mine? However you decide to do that. But all three of these are technically equivalent. I probably would use this one on my test. Okay. Just to force you to remember that x to the 1/2 is the square root of x. All right. What is different about letter B?
It's
It
common
doesn't
log.
have a base. Well, it
Oh, it's common log.
Yeah.
So what is the base?
Log 10.
Yeah. So good. That's good. So it does have a base, and it's base 10 since nothing was. Bases cannot be 1. We went through all this. The base is not allowed to be 0.
Oh, yeah.
It's not allowed to be 1. It has to be greater than 0 and not equal to 1. Yeah. So there's all sorts of conditions on base, which come from our exponential function, our Superman graph. What else is different about this function here?
Distribute.
You have to distribute. Very good. Don't work with things when they're in parentheses like this. And you have to be a little bit careful. But on something like this, I definitely want to distribute my 2 and distribute that negative 1/3. So be very careful. You want it fully expanded. So I'd write 2 log of x plus 2 times log of y minus 1/3 log of a. What happens here? Plus 1/3 log of b. So definitely we want things fully expanded so that we can condense them properly. And I'm just trying to save you aggravation. That's all I'm doing. So any number in front, we can kick it back to its power position. Getting to ignore the signs this time. And then I'm going to go ahead and write my single logarithm of an argument here, a numerator and denominator, and we just get to decide what goes on top and bottom. So this first argument here is x squared. Does it go on top or bottom? Top, because it had a positive in front. This is y squared, top or bottom? Top. This was a to the 1/3, top or bottom?
Bottom.
Why?
Because it's
Negative. Okay, so that's a to the 1/3 in the denominator. And this is b to the 1/3?
Top.
Good. And this is a great answer. And if you wrote it x squared y squared times the cube root of b over the cube root of a, that's also a totally acceptable answer. Either one of these is great. Yeah, AJ.
So you say both of them are good. Like, when we're doing a test, which one would you more often put as the answer?
Probably the one where I'm going to force you to remember more.
Okay.
Okay.
So
That's
That's the way I read it.
Yeah.
So.
we start off writing for B. We start writing the problem.
Like this.
Yeah.
Yeah, absolutely. Same idea. If the original problem in the book looks like this and you want to do a step in your head before you write it down, totally fine.
And I write it as log 10 times x squared times y squared.
Oh, just go directly to the answer? Yeah, some are going to be that easy. Yeah.
Well, it
I'm totally fine with this. Like, literally do as little work
like
as
the
possible.
log extended.
Yes. Oh, yeah, you could. With all the... Yes. Okay, so how do we use that? So there is a reason, the really important reason, that we have to learn how to expand and condense logarithms. Oh, thanks.
You're recording.